So, hello dear audience, I am Dr. MANOJ GUPTA, Assistant Professor in the Faculty of Engineering and Technology of Swami Vivekananda Subharti University. So, dear students, I am going to teach you the engineering mathematics. In this syllabus of engineering mathematics, I am going to take up a very important topic, and that is the elementary transformations. Here, we will discuss not only the elementary transformations, which is also known as the E operations. Also, its very important applications like how to find the inverse of a square matrix by using the Gauss-Jordan method. We can also use this elementary transformation to find the rank of a matrix, which is further used to test the consistency of the system of simultaneous linear equations. So let us start the topic. So this is the first one. This is the elementary transformations or operation, which is also known as E transformations or E operations. Mainly, this topic has important 3 steps we have. Any of these 3 steps is known as the elementary transformation. Okay. So let us understand the very first step. So the first step says that if we interchange any 2 rows or any 2 columns, this is a elementary transformation. This is the first step. So you can easily see that suppose if the ith row is represented by Ri and jth row is represented by Rj, so we can use this type of notations for interchange of for the interchange between 2 rows, and similarly if we are interchanging between the 2 columns, then we can write it as CIC. So this represents, we don't need to write that interchanging the ith row and jth row or ith column or jth column. What we will do, we will simply use this symbol, and this symbol will mean that we are making the interchange between the 2 rows or between 2 columns. So this is the very first step. Now the second step says okay. So now the second step says So this was the first transformation. Now the second step is that the multiplication of any row or any column by a non-zero scalar quantity. It says that we can multiply any row or any column and then by k. Here k represents a non-zero scalar quantity. If we multiply any row or any column by a non-zero scalar quantity, it is not going to change the properties of the matrix. So this was the second step, and now so this was the second step, and now we have the third step. In this third step, what we do here, we can multiply any row or any column by a non-zero scalar quantity, and then we can add this particular row or column to any other row or column. So it is written that the addition of a constant multiple of any row or any column to another row or another column. Like if we are multiplying the any row, like jth row, we are multiplying the jth row by a square quantity k, and then what we will do here, we can see what we are going here. Suppose if we have the ith row, okay, so it means that we are multiplying the jth row by a non-zero scalar quantity k, and then we are adding to another row ith row. So it represents a elementary transformation. Similarly, we can use the same operation also on the columns. So these are three important steps. Let us recall in one. We can summarize the whole steps of the elementary transformation. That is, firstly, we can interchange the any two rows or any columns. The second step says that we can multiply any row or any column by a non-zero scalar quantity, and the third step that we can add the constant multiple of any row or any column to another row or another column. These are three important steps. Any of these three steps is known as the elementary transformations. So after understanding the concept of elementary transformation, we can move ahead. But before that, I am going to tell you some very important property. Like it says that the elementary transformations does not change the order or the rank of the matrix. It means that it does not change. Whatever you can say, you can perform a number of operations of the elementary transformation on the given matrix, but in no way it is going to change the order of the matrix. It means it will not change the number of rows or columns, or similarly the rank of the matrix. So what is the rank? We will discuss it in the coming lectures. What is the rank? What the rank of the given matrix is. So firstly, we are going to take up some important applications. The first application is the inverse of a square matrix by using the Gauss-Jordan method. This Gauss-Jordan method is also known as the inverse of a square matrix by elementary row transformation. So let us understand the concept of C. So this is the method, Gauss and Jordan method, which is used to compute the inverse of a square matrix by using the elementary row transformation. It is to be noted that we have to use only and only elementary row transformations, not a single column transformation is allowed here. We have to make sure it. So what is the step? What are the some steps? Let us understand it. Suppose if we have a square matrix A, so what we will do here, by using the square matrix A, firstly we will write this step, A equal to I into A. It is written by using a property of the square matrix. It says that if we multiply a square matrix by an identity matrix of the same order, the result will be same. Okay. So this is the important result which we are going to use here, A equal to I into A. Now in the second step, what we do here, we apply on, you can see there are two A's on one on left hand side and the second on the right hand side. So what we do here, we use the elementary transformation only on A on left hand side, and the same operation which we are going to use on I, that is the I means the identity matrix of the same order of which the given matrix is. So So here we are not going to do anything with this A on right hand side. We will just return its values. So we can see this is the first. This is the second step which I am going to tell you that here we apply the elementary root transformation C on A. So when we use the elementary transformation on A, now the main thing is this is a very common question which comes in our mind, that what we are doing and why we are doing. Okay, so why we are applying the elementary transformation on A on left hand side. So the purpose is to make this A on left hand side into an identity matrix of the same order. The purpose is this one. So A will become I of the same order. So when we will apply the elementary transformation on A on left hand side, the same will also be applied on the right hand side, that is on I only, and this I will take another form. Suppose it becomes B. So the A on left hand side becomes an identity matrix and I on right hand side becomes another matrix B, and the second A on right hand side, it will be same, no change at all. Okay, so here it becomes I equal to B into A. So here we are going to use another important property of product of matrices. It says that if the product of any two matrices gives us an identity matrix, it means that the both the matrices are the inverses of each other. Like B is the inverse of A and A is the inverse of B. Okay, so A will be the inverse of B. But what we are asked to find the inverse of A. It means the inverse of A will be B, and this is the result. So these are the steps which we are going to perform in the following example. So let us understand the whole concept again in this example. So we can very easily see. So this is the example. See. So what we are doing? This is a very simple matrix which is of order 3 by 3 order. So we have to find its inverse. So as I have told you that what will be the first step? The first step is very simple. Simply write A equal to I into A. Remember one thing very clearly, that we don't have to write here A into I. It will violate the property of elementary transformations. So when we are using this type of operations, here we will have to use the elementary column transformations. Okay. So whenever we are using the elementary column transformations, we will write A equal to A into I. But whenever we are going to use the elementary row transformation, we have to use A equal to I into A. Remember this. So this is a very important. So what we do here now? So just put the value of A on left hand side and the value of I. So here, as you know that I just told you that I is an identity matrix. So the question is, what should be the order of A? I. So the order of I should be the same of which the given matrix A is. Since our given matrix is of third order, so same way we have to take the identity matrix of the third order. If A is of second order, then we have to take the I of the second order. Okay. So now this is the first step. Now we are going to use the elementary transformation. So as you know, I have just told you that we are going to apply the elementary transformation, but how we are going to use it? So the purpose is to convert the left hand side matrix into an identity matrix. So see, this matrix A will become an identity matrix, and you know how identity matrix looks like. Okay, see, so this matrix here is going to take this form. So firstly start with the diagonal elements. So diagonal elements means from here we have to take up this one. So if I say, if in the address form, if we write, it can be written as A11, A12, A13. Okay. So this is the A21, A22, A22, A23, A31, A32, A33. In the address form, this matrix looks like this. So what we do here, we try firstly we convert the first diagonal element A11 into 1. So we have to make this A11 into 1, that is here. So what we are going to do, we have to make this element 1. See, in our example it is already 1, so we don't need to bother for that. But suppose if it is not 1, it may be any other element. So what we will do, we will think over that how we can make this element 1. The step is very simple. Just firstly observe in the same column if there is 1 in any other place. If there is, then just interchange the first row with the another row where the 1 lies. But suppose if nowhere is 1, so what we will do? We will again think that how we can make it 1 by adding, subtracting, dividing. Okay. So if nothing comes in your mind that how to make it 1, just simply divide the whole row by the same number. Suppose if this is 2, so what we will do? Just divide the first row by 2. Okay, and it will become 1. So here in this example it is already 1. Okay. So now we have made it 1, suppose. Now the second step is what we will do. After making this diagonal element 1, we will make the other elements 0. Okay. And how we make it 0? By using the first row. So by using the first row, with the help of the first row, we are going to make 2 and 3 0. Okay. Suppose so suppose we have 1, we have 1, we have 1, and we have to make 2 0. How we will make it 0? How? By subtracting 2. This 2 can be written as 2 into 1. Okay. So we are going to use the same thing. So what we will do, we will multiply the first row by 2, and then subsequently we will subtract the subsequent row from the second row to make 2 as 0. It is written here. Similarly, if we have to make 3 0, so what we will do, we will multiply the first row by 3 and then subtract it from the third row. It is already written here. So by applying the same operation, so we will apply these two operations not only on the left hand side matrix but as well on the right hand side matrix, that is on the identity matrix. Okay. So let us do it. So I am going to explain you how this step is coming. See, suppose this is 2. So what it says, R2 minus 2R1. You can see here at 2 places R2 is written. What it means? It means here this R2 represents the new second row and this R2 represents the old second row. So what we will do, R2 minus 2R1. So what is R2? R2 means 2 minus 2 into R1. R1 means 1. If we solve it, 0. See, this is 0. Similarly, 4 minus 2, again R1, this is same one. No, this is R1. Again R1 is here 2. Again it will become 0. Again the next element is 5. 5 minus 2 R1. R1 means respective element is 3. So 5 minus 6, that is minus 1. So this is 1. Similarly, we can apply it on the right hand side, like 3, 5, 6. Suppose 3, 5, 6. We have to convert. So what we will do? R3 minus 3 R1. So this is the R3 minus 3 minus 3 R1. What is R1? 1. So it will become 0. So this 3 will become 0. This 3 will become 0. Similarly 5. So 5 minus 3 into R1. R1 means 2. This is minus 1. See, this is minus 1. Similarly 6 minus 3 R1. R1 means 3. That is 6 minus 9. That is minus 3. Minus 3. Okay. So this is the explanation of all the elements. In the same way, we can apply on the right hand side, and this identity matrix will take another form. So you can see that here the purpose was to make this matrix into an identity matrix like 1 0 0 0 1 0 0 0 1. So we have made the first column 1 0 0. Now the next target is the second diagonal element. In the same way, we will make it 1. You can see here that in this place there is no 1. This is 0. So what we have to do? We have to make this 0 1. And how we are going to do it? By applying the elementary transformism. As you know, I have just told you that if your desired element is not there, so what we will do? Just observe in the same column. Is there any place our required element is? So here we don't have 1, but we have minus 1. Just convert. So what we will do? Just interchange these two elements. See, just do it. What we are doing? Applying R23. R23 means that we are making the interchange between the second row and third row. It means the second row is going to take the place of third row, and third row will take the place of second. See. So what will happen? It will come here, and this will come here. See, 0 minus 1 minus 3 comes here, and 0 0 minus 1 comes here. The same thing happens here on the right hand side. So this was the next step. Now, but again, still it is not 1. It is only minus 1. So how we are going to make minus 1 into 1? By simply multiplying the respective row. It means that if we multiply the second row by minus 1, it will automatically become 1. So the same thing we are going to do here. So we are multiplying R2 by minus 1 so that it becomes 1. So the change will occur not only here but also here. So 0 into minus 1 is 0, minus 1 into minus 1, 1, minus 3 into minus 1, this becomes 3. And similarly, we have to multiply the third row by minus 1. Why we are doing it? As you know that we have to see, we have to make the third diagonal element 1 also. So, since it is already minus 1, we can do the same thing. So, here that's why I have multiplied the third row by minus 1 so that it becomes also 1. The same operation we are applying here on the right hand side matrix. Now, see here, it is 1 0 0 already, and again the second diagonal element is also 1. So, what we will do? Now, in the second column, we will make the other elements 0. So, 1 0 is already obtained, we have to make another element 2 into 0. And how we are going to do? By using the second row, we are going to make 2 into 0. So, here we are applying the transformation R1 minus 2 R2. It means we will multiply the second row by 2 and then subtract it from the first row. So, see, in the same way as I have just explained in the previous step, in the same way we can apply here. So, it becomes this. Now, so the first row, first column and second column elements are already telling us that it is a part of the identity matrix, but third diagonal element is also 1. So, what is the change? The change is here that the remaining elements minus 3 and 3 are not 0. So, we are going to make it 0. How we are going to make it? By applying this transformation. So, if we multiply 1 into 3, it becomes 3. So, 3 will be added here to make it 0, and this 3 will be separated from here to make it 0. So, the same operation. So, we are applying the third multiple of third row to R1, and it means first row, and subtracting it from the second row to make the desired elements into 0. See, so now you can clearly see, as we just get the left hand side matrix into an identity matrix, we will simply stop there. Now it clearly says that it is like I equal to B into A type, and I have just told you that what will be the A inverse? So, A inverse will be B. It means just the neighbor of A. Neighbor of A is the inverse of A. So, here the neighboring matrix is this one. So, this is the inverse of the matrix. So, these are the some important steps to compute the inverse of the square matrix by using the Gauss-Jordan method, or in another way we can say by using the elementary row transformations. So, this is the end of the topic, and I hope that you must have enjoyed this lecture, and see you in the next lecture. Thank you.